Is this working?
Yes.
All right. So, welcome everyone. Thanks for waking up. So many thanks to the organizers. It's been a stimulating week for me. So I'll talk about a statistical task known as non-Gaussian component analysis and how we can use it as a starting point to prove computational statistical trade-offs for a range of learning problems. So the high-level motivation for this type of problem, so I'm going to call it NGCA multiple times in the talk, is finding interesting directions in high-dimensional data. So if a direction is non-Gaussian in some sense, it's considered interesting. If it's Gaussian, it's considered noise. So what's the problem? So it's a distribution learning problem proposed in the signal processing literature. As the name suggests, the objective is to find a non-Gaussian direction, or more generally, a non-Gaussian subspace in a high-dimensional data set. So there is, of course, an assumption about the generative model, which I'll describe soon enough. So for this talk, we're only going to talk about subspaces of dimension 1, so hidden directions. Now, the problem has been studied fairly extensively from an algorithmic point of view. So here are all the references that I could find. So today we'll be showing some form of hardness and explore its implications. So far, I haven't defined the problem. So what do we mean by non-Gaussian component? So let me do this now. So definition number 1. So let V be a unit vector in d dimensions and A be a univariate density, probability density function. We define this distribution P parameterized by V and A, henceforth PV, to be the distribution whose projection in the V direction is equal to A and projection in the orthogonal complement is an independent standard Gaussian. All right, so note that all these PVs are product distributions, okay, with respect to a non-standard coordinate system. Now, what is the problem? So the NGCA problem is I give you A that matches the first M moments with N01, so M is a parameter of the problem as well. And now drawing IID samples from one of those PVs where V is hidden, the goal is to find this hidden direction. Of course, when I say find, I really mean approximate, let's say with respect to small angle or something. Now, the way that the problem is defined, it doesn't seem to be solvable algorithmically for various reasons. But for algorithms, usually we assume that, okay, the first M moments match and there is a significant difference in the moment of order M plus 1. Okay, so that's the problem definition. Is there a question about the problem itself? Yes.
No. A?
Yes, you can assume the algorithm is given a succinct description of A. And in particular, for the lower bounds I'm going to talk about today, this makes the lower bounds, stronger. All right, so the message of the talk is that this problem, NGCA, can be very useful as a starting point for proving lower bounds. How? By appropriately selecting this distribution A. Okay, by doing that, the NGCA problem captures interesting instances of several well-studied learning problems. Example, so note that PV has this form, it's a product of A in the V direction times a Gaussian in the orthogonal complement. So what happens if this A, if this univariate density is a mixture of Gaussians in one dimension? Let's say you have a mixture of 5 spiky separated Gaussians in one dimension. How would these PVs look like? Well, the claim that all of them would look something like this, like parallel pancakes in d dimensions, where all the means of the high dimensional Gaussians going through the V direction. Okay? And the only thing that's unknown here is the direction V. And note that finding V is basically equivalent to learning that GMM. If you know the direction, you can project and learn everything else, even if you don't know A. All right, and so let's go back to the general problem. So the first observation is that the sample complexity of this learning problem is polynomial in D and M. Okay, so there is a brute force algorithm that takes a net over directions, etc., etc. However, all known efficient algorithms, and by efficient I mean sample polynomial, they require at least D to the M samples dimension to the number of matching moments. All right. So the punchline of the talk is that this gap may be inherent. In particular, we provide some evidence for a large class of algorithms known as statistical query algorithms. So this is the informal theorem, but for any nice distribution A that matches its first M moments with the standard Gaussian, any algorithm that solves this problem either requires D to the M samples or has running time exponential in the dimension. And of course, any here has a star because it's not for any algorithm. Of course, it's for any statistical query algorithm something I'm going to define very soon. I'm sure that most of you have seen it. So as we'll see, the SQ hardness of this problem allows us to obtain a number of similar SQ hardness results. And in most cases, this provides the first evidence of hardness for a whole range of problems that superficially may seem unrelated to non-Gaussian component analysis. And these are some examples in the papers where they were obtained. So learning GMMs is going to be the running example for the talk, but there are many other problems that I'm not going to read. You can look at them and look at the references. And again, the point is that if you look at those problems superficially, they might appear very different from each other and certainly very different from non-Gaussian component analysis, but it turns out that we can view them in a unified way under the lens of this problem, okay? So I'm going to come back to that very soon. So let me, I owe you the definition of the SQ model. So what is the SQ model? It's a restricted model of computation for learning problems over distributions. Suppose that we want to learn some information about the distribution D. An unrestricted algorithm is going to take n IID samples from D, access the samples, and then do any polynomial type computation and give you the answer. The SQ model restricts the access to those queries. So we have access to some kind of oracle. We can ask questions, aka queries, about the distribution. This process is adaptive, and at the end, we get the answer. Now, what is this oracle? So it's, first of all, what's a statistical query? It's just a bounded function on the domain of the underlying distribution. And a statistical query gives you an approximation to the expectation of Qi. Qi is the statistical query under the distribution D up to some accuracy error tau that we're going to call the tolerance of the query. Now, there are other oracles in the literature, but this is not going to be important for this talk. The hardness results that I'm going to describe hold for most of these. Now, there are two complexity measures for an SQ algorithm. The first one is the number of queries. I'm going to denote it by little q. And the second one is the query tolerance. I'm going to denote by little tau. So a very rough sort of interpretation is that the number of queries is a proxy for the running time of a statistical query algorithm, and the tolerance is a proxy for the sample complexity. This interpretation is not super accurate for upper bounds, but it's quite useful for lower bounds. So let me explain why. So suppose we have proved this statement. So this is a mathematical statement we can prove. So suppose we show that for a given problem P, any statistical query algorithm that solves the problem either requires queries of tolerance at most tau, or maybe at least one query of good tolerance, or make at least q queries. Then this can be interpreted as follows. So any simulation of an SQ algorithm using samples for the problem P either uses at least 1/tau square samples or has running time at least q. So this is the interpretation we commonly use, and it can be viewed as a computational statistical trade-off in this model. And again, I want to emphasize that the first statement is a statement we can prove, and the second one in the dotted box is our interpretation of it. So are there any questions about the model? Yes.
Can you give us some intuition for how you get from tau to 1/tau squared?
Yeah, I mean, the statistical query is just a bounded function over the distribution, right? So basically, how many samples do you need in general to estimate the expectation of a bounded random variable with samples? You can take a bunch of samples and use the average, the empirical mean. So in general, this uses 1/tau square samples. Now, this square is not that important for the lower bounds I'm going to describe, even if it's 1/tau or any polynomial. 1/tau, it doesn't matter because the lower bounds I'm going to describe are super polynomial. But for more refined measures, this might be needed. Does it make sense? All right. So mandatory slide about the power of SQ algorithms. It's a restricted model. It's quite powerful. It captures many different algorithms. There is a prominent algorithm it doesn't capture. So we cannot learn parity sufficiently in this model. But for robust learning problems, it's a pretty good model. And in general, in particular, for all the problems I'm going to mention in this talk, all known algorithms with the strongest guarantees are in the model. Now, suppose we consider the following testing problem. So I give you access to a distribution D in R to the D, and I promise you that either D is equal to a reference distribution D0, or it's selected randomly from a family of distributions calligraphic D. And the goal is to distinguish between these two cases. Okay, this is standard hypothesis testing. And suppose we want to prove an SQ lower bound for this hypothesis testing problem. Now, there is a standard methodology to do this. If you haven't seen this before, I don't expect you to digest it in a minute, but believe me, it's something that can be worked out if you sit down for a few hours. So how do we prove SQ lower bound? So we need an inner product on probability distributions. So a natural one is the chi-square inner product. So we take the product of the likelihood ratios of P and Q, which are our two distributions, with respect to the reference distribution, and then we integrate with respect to D0, again, the reference distribution. Now, with this definition, it can be shown that to prove an SQ lower bound, it suffices to find a large set of distributions in the family D with large pairwise correlation. I'm not going to be more quantitative than this. And if we do that, then it follows that any SQ algorithm for the testing task either requires at least one query of high accuracy, or it requires a large number of queries. Okay, this is a black box result we're going to use. And the very rough intuition for the proof of this thing is just linear algebraic. So if you have a vector in a linear product space, it cannot have large inner product with many nearly orthogonal vectors under some assumptions. All right, that's the setup. Now, we have introduced enough background to formally state the theorem. So we consider the natural testing version of NGCA, where we want to distinguish the standard multivariate Gaussian from an unknown hidden direction distribution PV. So that's a problem. And the theorem is that if A, the univariate distribution that we use, matches its first M moments with the standard Gaussian, and it has finite chi-square divergence from the standard Gaussian, then any SQ algorithm that solves the hypothesis testing problem is in one of two categories. Either it requires a query of small tolerance at most d to the minus m times this chi-square distance, square root of the chi-square distance, or it requires exponentially many in the dimension queries. So that's the theorem. And of course, this is a hardness for the testing problem. As long as the distribution A is far from the standard Gaussian and satisfies some mild conditions, testing reduces to learning. So to show that learning is hard, suffice to show that testing is hard, and this is what this theorem does. So is there any question about the statement? All right, so let me move on. So I'd like to give you a little bit of intuition as to why this NGCA problem is actually hard. So the first one is an observation, okay, that just says that you cannot use low degree moments for this problem. In particular, like if you look at the tensors of order up to M of any of these PVs, they're identical to the tensors of the standard multivariate Gaussian. So really you need to go to tensors of order M+1, and these are very large multidimensional arrays, have d to the M+1 entries. It's not obvious how to exploit the tensor without actually using all of it. And the second sort of claim is a little bit less obvious. What it says is that actually random projections also do not help. And the corollary of that is that to distinguish, to solve the testing problem, essentially we need to use exponentially many random projections, unless we use very high accuracy, in which case we use many samples. Now this claim 2, is really the technical thing we need to actually prove the SQ lower bound. So this is the key lemma. Let me pass this. So take one of those PVs for an arbitrary, let's say, fixed V, and consider its projection in a different direction, the direction V prime, and look at this one-dimensional distribution. I'm going to call it Q. Then the lemma says that that Q is very close to Gaussian in chi-square distance. Okay, so the projection of PV in some direction of V prime is very close to Gaussian as long as V and V prime are not parallel, as long as they're nearly orthogonal. So let me give a little bit of intuition to that for that. So if V is a fixed vector and V prime is a random direction, the inner product is going to be something like 1 over square root dimension. So the right-hand side would be something like d to the minus m. This basically is the justification for like random directions failing. And as we'll see, we can do something much stronger than that. All right, so how do we prove this thing? So here is a picture. So we have V, the direction of PV, and V prime. Theta is the angle between them. So X is the distribution of PV. So here is PV. In the V direction, it's equal to A, and in the orthogonal complement, it's equal to a standard Gaussian. Okay. Now note that, and here is V prime. Okay. So note that if V prime is exactly orthogonal to V, then by definition, this projection Q is equal to the standard Gaussian, N01. So the lemma is a robust version of this fact. Okay. Now, how do we prove this? Now, the proof is analytic, and really the important observation here is that this Q, this projection, is just the Gaussian noise operator parameter theta applied to A. Okay, so if you haven't seen this operator, it's okay. We don't really need the definition. I'm not going to give it, but roughly speaking, this U theta of A is some kind of smeared out version of A. And because of that, in some sense, it retains the most prominent features of A, which are basically the low degree moments. Now, formally, the proof uses Hermite analysis. And a key sort of basic fact we need to use here is the eigen decomposition of this noise operator, which is a fact known for more than a century. All right, so now, given this lemma, the proof of the scalar bound follows relatively easily. So recall the goal is to find many of those PVs that are nearly uncorrelated, nearly orthogonal with respect to this inner product that I defined. So the first step is to select the family of V's. So to do that, we just select a set of nearly orthogonal unit vectors, vectors with inner product at least a constant, let's say, and we can find an exponential set of vectors satisfying this property. And the second step is to actually prove that any pair of such vectors V and V prime that have large inner products have small correlation. I say large, I meant small. Right? So, all right. So when two unit vectors are nearly orthogonal, V and V prime, then basically the distributions PV and PV prime are nearly uncorrelated. That's the statement. And here is the proof. All right. So the first equality just says that if you look at the correlation between PV and PV prime, even though these are high dimensional distributions, this is a two-dimensional quantity that depends only on the plane spanned by V and V prime. And therefore, we get sort of a two-dimensional or one-dimensional formula. Okay, this is we start from a correlation in high dimensions and we go to correlation in one dimension. A is a one-dimensional moment matching distribution. U theta of A is noisy version. And then by the lemma that I showed you in the previous slide, we can bound this from above by the inner product between V and V prime to the power of M times the chi-squared distance between A and the standard Gaussian. And from that, we're done. Okay, that's the end of the proof. Of course, each of these, the equality and the inequality require a little bit of work, but it's not that bad. So any questions about the proof before I move on? All right. So let's go back to the main scalar bound result. So the claim is that we can use it as some kind of recipe to prove similar scalar bounds for many learning problems. So how do we do this? So let's say we're presented with a generic distribution learning problem pi, for which we want to prove an scalar bound. So what we need to do is encode it as an instance of the non-Gaussian component analysis problem. So in particular, like we need to construct or prove the existence of a moment matching distribution A such that this PV that depends on A is a valid instance of the problem pi. Okay, that's the important thing. And in addition, we want to match as many low degree moments as possible. And of course, there is an additional step of bound of the chi-squared distance, which is usually okay. All right, so that's the recipe. And let me give you an example. Let's go back to learning mixtures of Gaussians. So the one-dimensional moment matching lemma is quite simple. I cannot say the same for some of the other applications. So let me parse it. So there exists a univariate mixture of K Gaussians with nearly non-overlapping components. So the components are going to be far from each other. That matches the first 2K minus 1 moments with the standard Gaussian. So A is going to look, So A is going to look something like that. And we construct it relatively easily. So we start by constructing a discrete distribution supported on K points that matches the first 2K minus 1 moments of the standard Gaussian. This is, you can use many methods to do that, like a clean way is using Gaussian quadrature. And after we have this A, this B, which is discrete, we rescale it and add, so convolve it with a skinny Gaussian to get A. This step is actually needed to get this finite chi-squared distance. So that's the construction. Okay, it's a univariate moment matching construction. And okay, this is A. How would the high dimensional distributions, how would the PV look like in the, sort of, using this particular A? So the claim is that the high dimensional distributions would look like parallel pancakes. So here is an illustration I'm very proud of, even though maybe I shouldn't. So the only thing that is unknown here is the hidden direction V. Okay, and if you have V, you have a distribution because you know A, and you also know, basically because you know A. Okay, the SQ bound says that basically it's hard to find V or to approximate V, which implies that it's hard to solve the learning problem. So this is an instance that actually I think Aaron also mentioned on Tuesday. Okay, this instance comes from this paper. All right, so it seems that I'm on time. So so the same recipe can be used for many other problems. So that's the punchline of the talk. I'm not gonna go through any other one. The techniques we would need in some of those cases to do the moment matching are quite different. In some cases, it's impossible to do it. So we need to do other things. I think Dan will gonna talk about one of those cases where it's actually impossible to do moment matching. So what do we do? So let me conclude. So I talked about non-Gaussian component analysis that I consider a central problem to study and prove that's actually computationally hard. So it's a natural starting point for hardness results. So the obvious open problem is find alternative evidence of hardness. So we know this problem is hard in the SQ model, but we don't know other models in which it's hard. So the interesting fact for me, that I'm mostly an algorithms person, is that for a range of problems, viewing those problems through the lens of NGCA gives you the first evidence of hardness. So these are not problems for which we're really convinced that this is the answer we're trying to prove. We didn't know anything beforehand, and this model allows us to give some evidence of hardness. If you want stronger evidence, you can try to prove it. Yes.
But you were saying that SQ model almost captures everything.
It doesn't capture everything. It captures many things, doesn't capture everything.
So other than Gaussian elimination, which you put it aside, what is the reason?
I mean, it is very, so roughly speaking, like algebraic algorithms that do operations on the samples are something that the model cannot do. In general, like if you come from TCS, the fact that you cannot find an algorithm explicitly that does it doesn't mean that there is no algorithm, right? In particular, for example, an SQ lower bound does not logically imply a lower bound in the SOS model. Okay, there are sort of subtle reasons for that. But as I said, alternative evidence of hardness is the first sort of direction. So for a couple of the problems that we have shown hard in the SQ model have been progress on this. For example, Guy with his student Matt Brennan proved that robust sparse mean estimation, which is a problem that we have shown hard in this model, in the SQ model, is actually hard based on the reduction. And also for learning GMMs, there is a sort of new reduction from some version of learning with errors, a continuous version of that. And the interesting fact for me is that in fact, the hard instances are essentially identical to the SQ hard instances. So basically, one can use the SQ hard instances as gadgets to do reductions. So a natural question to ask is how general is this phenomenon? Can we do this for other problems? In particular, for many of the other problems we show hard in this model. And finally, sum of squares. Okay, I couldn't have this talk without mentioning that. So can we actually prove convincingly a sum of squares lower bound for this problem? Okay, there are some issues of how to define this, but properly. But I think it's a natural open question. It's doable. It should be true. Okay, I'm going to pay money if someone proves an upper bound. All right, that's it. Thank you very much.
Say how much money?
It depends what you prove. Right? It depends what you prove. Yes.
What's the conjecture exponent for the number of samples you need in terms of m?
It's d to some power of m, some linear function of m. So I'm not particular about constant factors because I care about the qualitative, like d to the m, because m is going to be large for the applications I care about. If it's 2, then yeah, you have to be more careful. But if it's super constant, it doesn't really matter. So, and if someone does this reduction super carefully, they would get some constant that might or might not be the right one, but we didn't bother.
Additionally, there's a trade-off between the constant in the d to the omega of m in terms of the number of samples and the 2 to the d to the omega of 1 in terms of the number of queries.
Right. Yes.
So is it possible to like write down a function of computational time to the sample complexity? So because so far your statement is like either a large sample size or
And this is a lower bound. It's not an upper, right? So it's not necessarily a characterization. It's a lower bound. So in principle, if you use like if you use at least as many samples, the algorithm could be linear time, right? But otherwise, it has to use you have to use exponential time. So am I addressing your question or yeah? So I should say that the SQ model is a well-defined model of computation. So there is a notion of statistical query dimension that gives you not only lower bounds but also upper bounds. Okay, but this is not needed for the talk, and we have made the talk sort of unnecessarily complicated. Okay, so in contrast to low-degree polynomials, for example, SQ complexity also always gives you an upper bound on the SQ complexity of that problem. So in fact, we haven't shown upper bounds here. We have only shown lower bounds. We have shown that some instances are hard, but this doesn't mean that these are the hardest instances. Now, for many of those applications, it turns out that they are the hardest instances because they're matching upper bounds, not only SQ algorithms, but actual algorithms.
I mean, for the non-Gaussian component analysis, you can basically get matching upper bounds by just computing the m plus first moment tensor and noting that there'll be a difference between it and the standard Gaussian in the direction v.
So this is how the algorithms for that problem work, some of the algorithms that predated. So another thing that I want to say is, I guess since there doesn't seem to be more questions, is that when we wrote this paper back in 2016-17, we didn't know that this problem existed. So the word non-Gaussian component analysis does not exist in our paper. Subsequently, we realized that this exists in statistics. So this presentation is slightly different for that reason. Yes.
What's the issue you were referring to at the end with formulating SOS?
I mean, I'm not the right person to answer this, but I'm going to tell you what the people who are there, people have told me. So if you have a constraint satisfaction problem, there is a canonical SDP you try to enhance using this hierarchy. For this problem, no one has actually done this. So you can start from a natural formulation and try to prove lower bounds for that. But this doesn't necessarily mean that if you change the formulation in ways that are non-obvious, it would give you the lower bound would apply. That's the issue. Yes.
So you know this lower bound like rules out like GFOMs like we discussed last talk and Yankee algorithms? Because I think the SK algorithm of Andrea did something slightly non-trivial for the case like n equals 2.
All right. So this is a question I think we need to discuss offline because I'm not familiar with. Certainly, SQ algorithms sort of rule out gradient descent based algorithms, not arbitrary SGD, but gradient descent algorithms that basically approximate the gradients in every step. But it can be subtle, so we can discuss it offline. The answer is if you believe that low-degree polynomials rule out your upper bounds. So this, by recent paper, this implies similar low-degree test lower bounds. So maybe that's the answer. But I'm not familiar with this family of algorithms you're referring to.
All right, I guess we can move on to Daniel's talk.
Thanks.
Hi, welcome.